Today is Saturday, 14th of June 2025, 6 a.m. Eastern Time. This news is brought to you by Preeti Capital.
Welcome back to the deep dive. Today, we're looking into some really fascinating source material you sent our way, all about CERN.
Yes, the Large Hadron Collider specifically. And there was one headline in there that really catches the eye.
It absolutely does. It sounds, well, almost unbelievable. Scientists at CERN made gold.
Right. It immediately makes you think of, you know, alchemy, that ancient dream.
Exactly. But this isn't some dusty old manuscript. Your sources are talking about cutting edge physics. They briefly made gold.
That's the core claim, yes. A fleeting creation of gold atoms reported in the material. It's quite something.
Okay, let's definitely unpack this because, I mean, obviously they're not suddenly swimming in gold bars over there.
No, not at all.
So our mission for this deep dive is to really dig into these sources, figure out how they did it, what extreme conditions this needed, and maybe most importantly, what does this tiny fleeting act actually tell us about the universe, I mean.
Precisely. It's not about the gold itself, is it? It's about the physics, the knowledge gained from managing to create it, even for, an instant.
Right. It's a window into something much bigger. Okay, so let's start there. That core fact. They made gold. How is that even possible at the LHC?
Well, the method described is pretty incredible. It involves lead ions.
Lead ions. So lead atoms, but missing electrons.
Exactly. Just the heavy nucleus, basically.
Yeah.
And they accelerate these ions to speeds incredibly close to the speed of light.
Okay, so super heavy things moving at like almost unimaginable speeds.
That's the first part. The next step is they collide them head on.
The energy involved must just be astronomical.
Oh, absolutely. The sources mention temperatures in the collision zone hitting billions, possibly even trillions of degrees Celsius.
Trillions. I can't even picture that kind of heat. What happens in that environment?
Well, this is where it gets really fascinating. Creating that kind of energy density and temperature allows them to basically mimic conditions from just moments after the Big Bang.
Wait, so they're making a tiny temporary piece of the very early universe in Switzerland?
In a way, yes, a very, very small piece for a very, very short time. These conditions are so extreme, so energetic, that the rules change fundamentally. Atomic nuclei can be broken apart and reformed in ways that just don't happen otherwise.
And energy itself plays a role here. You mentioned E-MUPAs earlier.
Yes, exactly. Einstein's famous equation is key. The sheer kinetic energy of those colliding ions is converted into mass and energy within the collision zone.
Okay.
This energy fuels the whole process. It creates this chaotic environment where the fundamental building blocks of matter have enough energy and, well, freedom to rearrange themselves.
Right, so you get this incredibly hot, dense state from smashing lead ions, but how does gold emerge from that? What's the specific process?
Okay, so when those lead nuclei smash together, the protons and neutrons inside them basically come undone. They're not neatly packaged anymore.
It's like everything gets ripped apart.
Into its most fundamental components, yes. The sources describe a state called a quark-gluon plasma, forming for an incredibly brief instant.
Quark-gluon plasma. Okay, what is that?
Think of it as a super hot, super dense soup. A soup made of quarks and gluons, the particles that normally make up protons and neutrons, but they're briefly free, not bound together.
Wow. So the actual stuff that makes up atoms just floating free.
For a tiny fraction of a second, yes. It's a state of matter thought to fill the entire universe just microseconds after the Big Bang.
Okay.
Now, this plasma state is incredibly unstable. It cools down almost instantly. And as it cools, the quarks and gluons have to recombine to hadronize back into protons and
They
neutrons.
snap back together.
They do. But it's a chaotic process. They don't always reform into the original configurations. It's like throwing Lego bricks into the air and seeing how they land. Sometimes they might clump together in a new way.
And sometimes that new way is gold.
Occasionally, yes. Through complex interactions and rearrangements, a combination of protons and neutrons can form that matches the nucleus of a gold atom. It's one possible, though rare, outcome of this recombination.
So it's taking matter apart to its basics, and then in the reassembly, gold is one of the things that can form.
Exactly. And what's really cool is that this whole process forming heavier elements from lighter ones or from this fundamental soup, it mirrors what happens naturally in the universe.
You mean like in stars?
Yes, nucleosynthesis in stars,
Yeah.
or in much more violent events like supernovae or neutron star collisions. They're essentially simulating cosmic element creation in the lab.
Okay, but you said fleeting. How much gold are we actually talking about here? Is it something you could even like detect easily?
Oh, no, not at all. The sources emphasize this point strongly. The quantities are absolutely minuscule, infinitesimal.
Like single atoms?
Potentially, yes. Maybe a few atoms formed in certain collision events, and they exist for maybe a yoctosecond, an unbelievably short time, before they decay or transform again.
So definitely not a practical way to make gold.
Absolutely not. Forget any commercial application. The energy you put in is orders of magnitude greater than any conceivable value of the gold produced. You need incredibly sophisticated detectors just to even infer that it was created by tracking the particles that fly out.
Right. Okay, so if it's not about making actual usable gold, why is this significant? What's the real takeaway here, according to the sources?
This is the crucial part. The value isn't the gold, it's the physics. It's what we learned from creating those conditions.
Okay, like what?
Well, firstly, it tells us a huge amount about nuclear physics, about the strong nuclear force.
The force holding the nucleus together.
That's the one. By pushing nuclei to these absolute extremes, seeing how they break and reform, we learn about the fundamental nature and limits of that force. It's like stress testing the very fabric of atomic matter.
Stress testing the glue of the universe. I like that.
Kind of, yeah. And secondly, as we said, it's a window into the early universe.
That Big Bang connection again.
Exactly. We get to directly study states of matter, like the quark-gluon plasma, that haven't existed freely since the universe was incredibly young. It gives us clues about how everything evolved from that initial hot, dense state,
So it's like experimental cosmology almost.
in a sense. Plus, it directly simulates the process's nucleosynthesis that created all the heavier elements we see around us today.
The golden jewelry, the iron in our blood.
All of it. It was forged in stars or cosmic explosions. These experiments let us study that forging process up close, in a controlled environment. It helps us understand our own cosmic origins.
That's pretty profound.
It is. And of course, there's the element of testing our theories. We have the standard model of particle physics, theories about nuclear interactions, about cosmology.
Right.
These extreme experiments push those theories to their limits. Do the predictions hold up? Do we see what we expect to see?
And if not,
Well, that's often where the most exciting discoveries lie. If the results deviate from the predictions, it might mean our theories are incomplete. It could point towards new physics beyond the standard model.
finding cracks in our current understanding.
Exactly, hints of deeper principles at work. So really, the gold isn't the treasure. The conditions needed to make it, and what those conditions reveal about fundamental forces, the early universe, element creation, that's the real prize.
That makes sense. It shows what the LHC is capable of, not just finding particles, but recreating these extreme cosmic environments.
Absolutely. It's a tool for exploring the frontiers of matter, energy, space, and time. It helps us piece together the grand story of the cosmos.
So to sort of wrap this up from the source material, this whole CERN makes gold story, it's not modern alchemy aiming for wealth.
Not the slightest. It's about fundamental science, using incredible technology to recreate moments from the dawn of time.
Yeah, to unlock secrets about particles, forces, and how the very elements that make up, well, us and everything around us came to be.
It's a unique perspective, powerful way to connect the incredibly small with the incredibly large, the instant after the Big Bang, with the universe today.
It really makes you think, doesn't it? Being able to essentially run a simulation of the Big Bang's aftermath right here on Earth,
Right.
connecting quarks and gluons to the stars, and makes you wonder what other cosmic secrets are waiting to be unlocked when we push these boundaries even further.